I'm going to talk about integrals of the form sine to the kx times cos to the mx, where k and m are natural numbers. I couldn't find the PowerPoint way of doing the actual natural number thing, so whatever. So yeah, let's do a bunch of integrals then. So I'm going to break it down into cases and then try and generalize some results and come up with some ideas. So firstly, let's deal with the case where either k or m is zero. In other words, such that one of these two terms goes away. It doesn't really matter which one. I'll deal with the case where sine goes away and just leaves me behind with some cos to the big power number. Now I've done integrals like this before on this channel. You can use reduction formulas amongst other things. I'm going to do it differently in this video just because I quite like showing different ways of doing it. I'm going to write the integral like this. Now, this is using complex numbers. Euler's formula e to the ix equals cos x plus I sin x is here. If you replace the x's with minus x's, you get this. Cos to the minus x is an even function, so it doesn't matter when you put a minus in here, so it just becomes cos x. Sine of x is an odd function, so this minus comes out to the front here. And now if we add together these two, the top and the third line, we get 2 cos x equals this plus this, divide by 2, and that's where I got this result from in here. You can, of course, do the same thing for sine. If you do this, take away this, and you'll end up with sine as this. So it doesn't matter that the cos is the one here. It could be the sine. I would just do exactly what I'm about to do with this one here. It wouldn't make a difference. Anyway, I'm going to binomially expand this thing here. After I pull out the half to the power 6, I can then binomially expand this thing here. It turns into this. A half to the power 6 is 1 over 64. I've left one of the 2's here because I'm about to put it back into all of this. What I'm going to do is I'm going to put all of the powers that pair up together to make this thing here. By the way, when I binomially expanded this, of course, 6 of those is e to the 6ix. 5 of those and 1 of those, the powers take away and you get 4 of them. 4 of those and 2 of those, you get 2 of them, and so on. It's just how that works. It's always going to work kind of like that. When you group them together, you get this. Now I can put the 2 into all of these things here to make this. And the reason that's really helpful is because this is, all of these 3 things are just definitions of cos. Cos of 6x, cos of 4x, cos of 2x. That's all super easy to integrate. So here's a method for integrating. It doesn't matter how big this number is. Of course, the bigger it is, the more annoying it's going to be to binomially expand that and then group everything together and then do a whole ton of integrals. But it's technically completely possible, and that's just one interesting way of doing that integral. Now, that's the most important result out of the way, and like I said, this would work for sine to the power because you just have the very similar thing here. It would all group together. You'd get a bunch of sines here. You get a bunch of causes down here. Fine. Now, what about though? So that was the case k or m was 0. What about the case where k or m is equal to each other? So this is a special case, kind of. So for example, sine to the 6 times cos to the 6x. So the case where the 2 powers are equal. Now this actually ends up being quite a nice case because you can say that this is sine x times cos x all to the power 6. And then if you use this result up here, sine times cos is a half sine 2x. So you can replace that here, and then once you bring the half out, this is the same as the integral that we just did. Like I said, it doesn't matter that there's a sine here instead of a cos. It doesn't matter that there's a 2x here instead of just an x. You can just use this formula instead. You can expand everything out. You can regroup things. You can integrate. It looks just the same as before. So if you've got the case k is equal to m, you can do this nice little trick. And theoretically, it all works out just the same as the example before. Now, what if you have different cases? So let's do the case either k or m is 1. It doesn't really matter which one. But let's do the case that k or m is 1. So let's do this one here. Now, this actually turns out to be the easiest of all the cases because this is just reverse chain rule. Because this is here as the derivative or of the form of the derivative of this one here. I can just say that this immediately integrates to cos x to the power 7, and then put a 7th here to make the 7 times the 7th just make a 1, which is what I've got here. And then, of course, cos differentiate is minus sine. So put a minus here to balance out the fact that there's no minus over here. There's a plus c, I guess. And that doesn't matter whether k or m is 1. Works the other way around just as well. You just get the same kind of idea. And that actually turns out to be the easiest case. So we've done cases where we've only got a sine or a cos. It doesn't matter how high the power is. Our little complex number integral will work a trick, will work just as well. Case where k is equal to m, you turn it into sine 2x and it all works out okay. Case where k or m is 1 is actually the easiest case. And now let's keep going. So let's say what happens if k or m is 2? So we have integrals of the form this. Well, here we can just say that sine squared of x, using this formula, of course, is 1 minus cos squared. expand this out, and we just end up with two integrals of the form that we know how to deal with. We dealt with them in the first question. It's certainly annoying because you'd have two of them to do, but it is certainly possible. Now, there are going to be more efficient ways of doing this, but I'm not really interested in the most efficient way. I'm just trying to find a way that would generalize for all results. So I'm just saying this would definitely work. It would just take a bit of work. There are better ways of doing it, but this is theoretically possible from here based on what we've already got. Impractical, but completely possible. Now, what if we just go uppercase? So we've dealt with that case. We can do it. Impractical, but what? I don't care. Let's go uppercase. Let's say that we've got a power 3. Now, this case is actually really nice because we can use a really, really nice little trick here where we break this sine cubed into sine times sine squared. And then that sine squared is 1 minus cos squared. And now I can just expand all this out and I get this. And this is the case we saw earlier with power 1. This just immediately integrates. It's really nice. And so sine cubed is a really nice case, or anything cubed. It would work just the same with cos. You just write cos into 1 minus sine squared into some more sines. You get just a single cos here. It would all be fine. It would be great. So that case was super easy to smash out. What about if we go even further? What about if k or m was 4? Now, this is an annoying case again because, okay, sine squared I can write, or sorry, sine to the 4 I can write as sine squared squared. Sine squared is 1 minus cos squared. So this becomes 1 minus cos squared, all squared. I can expand that out. I can expand that out. And we just end up with 3 integrals of the form of something that I know how to do. Again, this is immensely impractical, but it is theoretically completely possible based on maths that we know. And actually, that would hold for any even number here. Because even if it was like sine to the 10x, that would just be 1 minus cos squared to the power 5, because then it's sine squared to the power 5 is sine to the 10. So you just binomially expand that thing, you'd expand it with the remaining causes, and you just end up with a bunch of causes that you could theoretically, but impractically do. So actually, we've now come up with a way of integrating anything of the form sine k cos m if they're both even. You just take the lower one probably, and you replace it like this, and then you have 3 integrals to do that are all really annoying and difficult to do, but we can theoretically do them. What about if we go up to 5 then? And actually, this teaches us something really nice, that we can extend this idea that we used for 3 earlier. We can say sine to the 5x is sine times sine to the 4. Sine to the 4, as we saw before, was 1 minus cos squared all squared. But this is really nice because when you expand this out and expand it out some more, you end up with this lone sine, making all of the integrals super easy. In fact, I can just write it straight up on the screen right away. So now we've come to the conclusion that actually, if you're lucky enough to have either one of these two numbers be odd, the integral is super nice using this little trick. You can just pull out one of whichever one is odd, just pull out one of them to leave 2 even numbers, replace whichever one you want with 1 minus the other thing squared, all to the power of some number, expand it all out, and you just always end up with one trig function like this in every term. Super easy to integrate. And so that would hold for any odd number as well. So I think, therefore, where I think I've now dealt with any single integral of the form sine to the power kx times cos to the power mx, where k and m are natural numbers. The case where you've got at least one odd number is super nice, and this trick, I mean, bear it in mind because it could straight up come up. It's not a long thing to do. The case where there are 2 even numbers, I've theoretically laid out a way of doing, but it might be worth bearing in mind that there might be more efficient methods available. For example, I'm looking at this and thinking maybe I could write it as sine x times cos x all to the 4 times another cos squared x. And then I could use the sine 2x thing and then maybe do a replacement of the cos squared x with some more double angles. And maybe that would be a much more efficient way of doing this particular integral. But I wasn't really interested in that. I was interested in setting out a theoretical way that could solve all of the cases. And I think I've done that. So anyway, I thought that was quite fun. Thanks for watching, and I'll see you next time.